This is a video from section 12.5 in a Calculus 3 class. The examples will be taken out of the Stewart Calculus textbook, 9th edition. Recall, the distance from the point x sub 1, y sub 1, z sub 1 to the plane ax plus by plus cz plus d equals 0 is given by the following formula. Capital D is equal to the absolute value of ax sub 1 plus by sub 1 plus cz sub 1 plus d, all divided by the square root of a squared plus b squared plus c squared. The directions say to find the distance from the point to the given plane. And we're going to take a look at problem 71. The point is 1, negative 2, 4. The plane is 3x plus 2y plus 6z equals 5. Now, 3x plus 2y plus 6z equals 5 is not in the form of ax plus by plus cz plus d equals 0. And so if I subtract 5 on both sides, I get 3x plus 2y plus 6z minus 5 equals 0. And so we are going to find the distance from the point 1, negative 2, 4 to the plane 3x plus 2y plus 6z minus 5 equals 0. So in this problem, as you can see, x sub 1 equals 1, y sub 1 equals negative 2, z sub 1 equals 4, a equals 3, b equals 2, c equals 6. So I'm just reading off the coefficients of x, y, and z respectively. And then here, d equals negative 5. So capital D is equal to the absolute value of 3 times 1 plus 2 times negative 2 plus 6 times 4 minus 5, all divided by the square root of 3 squared plus 2 squared plus 6 squared. So you notice here it's just direct substitution. A is 3, x sub 1 is 1, b is 2, y sub 1 is negative 2, c is 6, z sub 1 is 4, and then d is negative 5. And then I'm dividing by the square root of a squared plus b squared plus c squared, but I just directly substituted the values for a, b, and c. So if I do the arithmetic calculation, I get capital D is the absolute value of 18 divided by the square root of 49, which simplifies to 18 over 7. And that's the answer to problem 71. If we take a look at problem 72, the point is negative 6, 3, 5, and the plane is x minus 2y minus 4z equals 8. So, of course, I have to subtract 8 on both sides. So this problem translates into the following. So the point is negative 6, 3, 5, and the plane is x minus 2y minus 4z minus 8 equals 0. So in this question, x sub 1 is negative 6, y sub 1 is 3, z sub 1 is 5. And then a equals 1, that's the coefficient of x. B equals negative 2, that's the coefficient of y. C equals negative 4, that's the coefficient of z. And d equals negative 8. And so it's just a direct substitution into the formula. So capital D is equal to the absolute value of 1 times negative 6 plus negative 2 times 3 plus negative 4 times 5 minus 8, all divided by the square root of 1 squared plus negative 2 squared plus negative 4 squared. And so you notice a is 1, x sub 1 is negative 6, b is negative 2, y sub 1 is 3, c is negative 4, z sub 1 is 5, and then we have our trusty d at the end. Small d, that is. And then if you notice, we're dividing by the square root of a squared plus b squared plus c squared. but I substituted the values for a, b, and c inside the radical. And so when we do that calculation, we get the absolute value of negative 40 divided by the square root of 21. And then, so d is 40 over the square root of 21. And then I rationalize the denominator. And so I multiplied the numerator and denominator by the square root of 21. And so therefore d, capital D, is 40 times the square root of 21, all divided by 21. Okay, and that's problem 72. Now the directions say to find the distance between the given parallel planes. And I claim these next set of problems are exactly like the first two problems. And so what I'm going to do is I'm going to pick a point on one of the planes and then find the distance from that point to the other plane that doesn't contain the point. You'll see what I mean in a minute. But it's basically going to mirror almost what we did in the first two problems. So on 73, we have these planes. 2x minus 3y plus z equals 4, and 4x minus 6y plus 2z equals 3. In the first step, we want to pick a point on the plane 2x minus 3y plus z equals 4. It doesn't matter, I claim, what point you pick. So we want to pick a point for convenience. And so what I'm going to do is let x and y both be 0. If I solve for z, I get z equals 4. So my point P is the point 0, 0, 4. In the second step, I want the distance from 0, 0, 4 to the other plane, which happens to be 4x minus 6y plus 2z equals 3. Okay? Pick a point on the first plane, and then calculate that distance from the point you picked to the other plane, which in this case is 4x minus 6y plus 2z equals 3. Okay? Now, so we have the point 0, 0, 4, and I went ahead, by the way, and subtracted 3 on both sides to make it look like the standard form for a plane we need. So over here, we have 4x minus 6y plus 2z minus 3 equals 0. So again, I want to find the distance from the point 0, 0, 4 to the plane 4x minus 6y plus 2z minus 3 equals 0. So in this problem, x sub 1 is 0, y sub 1 is 0, z sub 1 is 4. And then a equals 4, b equals negative 6, c equals 2, and d equals negative 3. So when I plug this into the formula, capital D is the absolute value of 4 times 0 plus negative 6 times 0 plus 2 times 4 minus 3, all divided by the square root of 4 squared plus negative 6 squared plus 2 squared. So again, if you notice, a is 4, x sub 1 is 0, b is negative 6, y sub 1 is 0, c is 2, z sub 1 is 4, and then d is negative 3. And so, again, I'm also dividing by the square root of a squared plus b squared plus c squared, where I'm substituting the values for a, b, and c. When I perform that calculation, I get 5 divided by 2 square root of 14. So if I rationalize the denominator, it turns out that d is 5 times the square root of 14, all divided by 28. And that's number 73. Let's take a look at 75. That's a really interesting question. Now, it says to show that the distance between the parallel planes ax plus by plus cz plus d sub 1 equals 0 and ax plus by plus cz plus d sub 2 equals 0 is given by the following formula. Capital D is the absolute value of d sub 1 minus d sub 2, all divided by the square root of a squared plus b squared plus c squared. Now, I'm going to verbally tell you guys something here. I'll write it as well. Keep in mind something. If A equals B equals C equals 0, right? This formula doesn't make any sense in the sense that we're dividing by 0, which we don't want to assume, okay? Which we can't, by the way. Then d sub 1 equals d sub 2 equals 0, okay? And so what that tells me is you're talking about the same plane and that d equals 0. So it's not very interesting. And so we're going to assume, for sake of argument, that one of the coefficients is not 0. And I'm going to assume C is not 0 for sake of argument. Now, A and B can be 0. And it turns out it doesn't matter. I just need C to not be 0. And also I want you to keep in mind, I could make this same argument if I assume A is not 0 or B is not 0. I just need at least one of them to not be 0. Okay. So in this problem, we're going to assume C is not 0. So we're going to pick a point on the plane AX plus BY plus CZ plus D sub 1 equals 0. And so I'm going to let X equal Y equal 0. So when I solve for Z, I get negative D sub 1 divided by C. So the point I pick is 0, 0, negative D sub 1 over C. And we translate this problem to finding the distance from 0, 0, negative D sub 1 over C to the plane AX plus BY plus CZ plus D sub 2 equals 0. So capital D is A times X sub 1, which is 0, plus B times Y sub 1, which is 0, plus C times negative D sub 1 over C, that's Z sub 1, right? Plus D sub 2, all divided by the square root of A squared plus B squared plus C squared. The denominator makes sense because we're assuming C is not 0. A and B can be 0. That's fine. As long as one of them is not 0, we're okay. And so capital D is the absolute value of D sub 2 minus D sub 1 divided by the square root of A squared plus B squared plus C squared. But I claim that's the same as the absolute value of D sub 1 minus D sub 2 over the square root of A squared plus B squared plus C squared. And so, therefore, capital D is the absolute value of D sub 1 minus D sub 2 divided by the square root of A squared plus B squared plus C squared. And we're done. And I want you guys to keep in mind something. If I take the absolute value of D sub 1 minus D sub 2, now let's factor out a negative 1 inside the absolute value. But that means I'm multiplying by D sub 2 minus D sub 1, okay? But this is the absolute value of negative 1 times the absolute value of D sub 2 minus D sub 1. But the absolute value of negative 1 is 1. And so this is the absolute value of D sub 2 minus D sub 1. And so therefore, the absolute value of D sub 1 minus D sub 2 is the absolute value of D sub 2 minus D sub 1. So I wanted to make a note of that. And that's going to conclude this video for section 12.5. We worked on problems 71, 72, 73, and 75. Thank you.